So, hey everyone, I'm Arec. I'm a former PhD student from Michael's lab, now working on optimization for subterranean problems at Terra, so critical mineral development and resource development. The topic we're going to talk about today, disciplined convex programming and then multidisciplinary optimization with Sydney. This disciplined convex programming chapter is super cool, and the techniques from it are very useful. I think it's a new add to the book, I think this term, but it's really cool. So it's a lot to cover, I think, in half of a lecture, but hopefully I think maybe in the next 45 minutes you'll get an appreciation for DCP and have a feel for like when it's useful and when you might be able to use it for your problems. And if you want to get more into it, I really highly recommend taking the Convex class, E364A, or even just watching the lectures online. They're very entertaining and funny. But yeah, cool. So let's dive in. So over the last, I guess, couple of classes, we've gone into linear programs and then quadratic programs. Both of these things are subclasses of convex programs. So a convex program is a problem that has a convex objective with affine inequality constraints, and then, affine equality constraints, and then convex inequality constraints in the form of convex less than or equal to 0 in standard form. This is cool for a bunch of reasons, and very nice for optimization for a bunch of reasons. First of all, local minima are global. So once you get to the bottom of a bowl, you know that that's just the right answer. Under mild assumptions, you get strong duality. So you get that the primal optimal P star is the dual optimal D star, which means you can use primal dual methods and then get dual certificates that tell you when you're done. When you combine these things together, what it means is you get efficient and exact solution methods to a wide range of problems that are in this convex program class, similar to LPs and QPs. And that ends up meaning that you get reliable solutions to many important problems, and particularly problems where you might need solutions to come in at, like, say, 100 hertz, and you might need to know that the answer you get is the best answer, like things in finance or in control. Convex optimization ends up being a really useful tool to handle these problems. What we're going to talk about today is a subclass of convex programs called disciplined convex programs. These are programs that can be automatically verified, so that's the subject of 14.2 on how that's done, converted to a canonical form, and then easily solved. What's really nice about this class of programs is that it's very easy to kind of, if you can show that you fit into this class, and it's very easy to come up with a solution using disciplined convex program methods and solvers. Here's an example of what that looks like. So say you have this convex objective and convex constraint here. It's not an LP, not a QP. Maybe you can solve this with gradient descent with some penalty methods, or come up with some other solutions there. Alternatively, if you use disciplined convex programming, all you have to do is import the DCP package, Convex in Julia, CVXPy, in Python, import a solver, SES, specify your problem in what looks like a very human-readable form, so to minimize the objective given the constraints, and say solve. And in a couple of iterations, and maybe 1/10 of a second, you'll get what is just the right answer. So you'll get the answer that the X star falls on this constraint circle in white and is as close as possible to the yellow diamond there. And importantly, you can do this for any problem that falls into this DCP program category. So let's back up a bit. Maybe this is some review. So what are convex sets? Convex sets are sets where every line between points in the set also lies within the set. So things like points, lines, half spaces, balls. But also intersections of convex sets are also convex. So that gets you things like orthants and quadrants, polyhedra, other cool shapes. And the things on the right definitely are not convex, right? You can draw these red lines, and these red lines leave the set, so you know these are non-convex sets. Similarly, convex functions are functions where every line between points on the function lies at or above the function. So lines are both convex and concave. So concave is the same but for below the function. Things like quadratics and also the max of different convex functions are also convex. You know, if you picked any 2 points on the white lines, drew a line between them, that line's going to be at or above the function. And then for the example on the right, definitely not convex because we cross over and go below. So a lot of things end up being convex. So things like in single variables, things like affine, things like powers for p is less than 0 or greater than 1. So things like 1 over x, things like x squared. Exponentials, entropies, ReLUs, and a bunch of things also end up being concave, like powers between 0 and 1, like square root, and like log. So these are just some examples. For multiple variables, things that end up being convex include, again, affine functions of multiple variables, quadratic functions with positive semi-definite q. If you have negative semi-definite q, then those functions will be concave. Things like norms, so all norms, sum of squares, and pointwise maximums, log sum x, and then you have things like geometric mean being concave. So a lot of things that end up being convex that immediately you can plug into a convex solver and get the right answer for. Okay, so what about establishing convexity in your own functions? So one way to do it is to maybe just verify that definition manually. So you have some function, maybe you just sample some endpoints, sample the points between them, make sure they're always on top. That's like one way to do it. Maybe it's not a very robust way to do it, as you can imagine. If you're in multi-dimensions, you might take slices and do the same thing, but you can often end up maybe missing pieces. If your function is twice differentiable, you can check that the Hessian is positive semi-definite everywhere. This might be easy for things like quadratic functions, where it's equivalent to just checking if that q is positive semi-definite, but it can often be more difficult. And what the topic of today in this chapter is going to be is building that function f from simpler functions using rules that preserve convexity. And these will be the rules that specify if something is DCP compliant. And luckily, it's only 2 rules. So if your functions and expressions and constraints satisfy these 2 rules, you can plug it into one of these solvers. Those 2 rules are sign rules for product-free expressions and additional rules for composition. So we'll go over these rules in some detail here. Okay, so first up, sign rules for product-free expressions. So rule number 1 states that all expressions that go into, say, other functions, as functions get composed together, all of these expressions have to be product-free. So they have to look like this. So you can have things that are affine in your problem variables on the left, and then add together linear combinations of other functions where you know something about the convexity or concavity of those other functions. But you can't have, for example, additional terms that take products between different functions. Given this rule, we can say that this overall expression, an overall expression that looks like this, is convex if for each of the functions, j, either f of j is convex and the coefficient outside it is non-negative, or the expression or the function is concave and that coefficient is non-positive, or that function is affine. So what does that mean? If I wanted to sum together, say, something that was affine along with exp, So exp of x, so that's exp of x here. What coefficient would I have to put outside of this x so that the resulting thing has a bowl that goes up? So what would the sign have to be for C here? Yeah, positive. So if it's positive, then this thing ends up looking like this, right? And then that resulting thing is convex. So that's all this rule is saying, is that when you sum together things that are convex, you preserve convexity. When you sum together things that are concave, you preserve concavity. Okay, so for these same set of rules, you can negate these to get the rules for concavity. And then you can also say that this expression is affine if all the f's are affine, and constant if all of the functions are constant and the b's, the things outside of the actual variable terms, are 0. So that's it for sign rules, for product-free expressions. Now, why can't we add products here? Just in general, knowing if two expressions are affine or convex and concave doesn't say anything about their product. So think of even just x1 times x2. That's going to look something like this, and that's immediately, even though those two things are affine, that thing is immediately non-convex. Now, that doesn't mean that the expression won't be convex or concave, just that we can't easily check using our DCP construction rules. Great. So that was the first set of rules. Now the second set of rules, a little bit more difficult to visualize, but they're composition rules. They say what happens when we compose two functions together. So for univariate functions, so f of g of x, where f just takes in one variable, we can say that the resulting composition is convex if f is convex and either f is non-decreasing over the range of g and g is convex, or if f is non-increasing over the range of g and g is concave. Similarly, to show something is concave, we can flip these rules around. With the asterisk here, that we need to make sure that the range of g is within the domain of f. So for example, if f was square root, that g wouldn't spit out a negative number. So let's look at some examples. So here are two examples that, if you visualize them, they're both visually convex. Let's see what the DCP rules tell us. So starting with the one in red, exp of sine x, we have that f of x is exp, g of x is sine x on negative pi 0. So I'll just say on negative pi 0, that's a convex function. That's going to look like this. And then after 0, it's going to do like that. And for negative pi, it's going to do like that. But over here, it's convex. We have that f is convex and non-decreasing, right? Exp of x doesn't decrease as you increase x, it goes up. And we have that g is convex. What does that tell us about the composition? Just according to these rules. Convex. So by the first rule here, this thing is going to be convex. Okay. Now going down below, f of x is square root. G of x is exp. We have that f is concave and non-decreasing, and g is convex. What does this tell us about our function? Nothing. So f of g of x is unresolved by these DCP rules. So we would not be able to plug in square root of exp of x directly into DCP. We would have to define some other thing to show the convexity of that expression square root of exp of x. Again, so DCP is sufficient to show convexity, but there are things that are convex that can't be represented with the DCP rules. Okay. So that was univariate. Moving on to multivariate, so functions that now take in multiple values. We have a similar set of rules, but now these rules one of these rules have to hold true for every variable in the expression. So we can say that this multivariate expression is convex if f is affine or convex, and then for each of the variables, one of the following holds: either f is non-decreasing in that variable and that, in that expression, and that expression is convex, or f is non-increasing in that expression and that expression is concave, or that expression is just affine. And similar set of rules for concave. And if all of them are affine, then you can just say the resulting thing's affine. Okay. And that's it. That's the two things to know if you can just use these tools out of the box. So with that, I think let's go through an example and see kind of how these two rules can get composed together to check something more complicated. So the thing that we're going to check is whether the following here is convex. Let's do x1 plus 3x2 plus max of exp of 1 minus log x2 plus x1 squared, comma x1 minus x2. So this is a pretty, wild thing here. We know this piece is affine. So we really just care about checking this second piece here. To check this, I think it might help to set up a tree of the expressions so we can kind of recursively go through and check these composition rules. So I'll just set that up here, and then we can do the composition together. So we have the following. We have a max over two things, x1 minus x2 on the left. And then we have a plus over two things, x1 squared, and then an exp over 1 minus log x2. Okay, great. So I'll start us off to say x1 minus x2 is just affine. What is 1 minus log x2? Convex. So they're going to follow by our product-free composition rules. This is a product-free expression. We have a negative on a concave function. Log points down. You flip it up. Now this whole thing is pointing up, and this thing is convex. What about x1 squared? You can scream it out. Cool. It's convex. Okay, now what about e of a convex function? So mind you, e is looks like this. So it's like convex and then non-decreasing. So now what's e of a convex function? Does everyone follow? It's convex based on this first rule. This is going to be convex. What's the sum of two convex functions? Convex. And then we have max over a convex and an affine thing. So max is a multivariate function that is going to be convex and non-decreasing again. If you increase any value of x, the max, or any value of any variable in a max, and the resulting is only going to go up, or it's not going to go down, so it's non-decreasing. So we have, again, a convex, non-decreasing thing of a convex and an affine. What's that? It's convex. Okay. So that is to say that using our DCP rules, we can establish that this whole expression is convex and then plug it into a DCP solver, and yeah, great. I want to do one more just to highlight a point here. What about square root of 1 plus x squared? 1 plus x squared here is going to be convex. Now what about square root of a convex function? Cannot say. This is unresolved. Right? This is not any of these rules. Now what about the equivalent problem of norm 1 comma x? You have that 1 is constant, x is affine, norm is convex and non-decreasing in each of these elements. So by that, these things are resolved by DCP, and now this is convex. Now, this is kind of weird. So that is to highlight that it's up to you to take care in how you specify your functions, because different ways of specifying them might lead to different DCP compliance or non-compliance. So yeah, that's just something to keep in mind. Okay, great. And with that, that's it. That's like all you need to know to plug to see if the things you're trying to optimize over are convex. And then you can just specify them in the way that was done in the third slide here and then get your answer. Great. So I think for the second half of these, I think we want to go into what's actually happening behind the scenes of a DCP solver. So how does that happen? How does the verification happen? What's happening in canonicalization? And what are some ways to do this kind of easy solving? Okay, so good news is you guys already know how verification works now. It's exactly the example that we just did together. Behind the scenes, form an expression tree using in some atom library of the things that you already know, like x spin log x, spin max, and norm, and go recursively up this tree and automatically verify if the things are convex. So an atom library is just the base symbols from which complicated affine, convex, concave expressions can be constructed. So it looks something like this. So for each atom, we track important features like the curvature, so it's like convex for what, concave for what, its monotonicity, its range. And what's cool is that domain experts can then introduce more and enhance the capabilities of the actual library itself. So if you know, for example, I mean, ignore the norm piece for a bit. If you know that square root of 1 plus x squared is convex, then you can say maybe introduce that as an atom, and someone can use that atom in their construction. That's great. So given these atom libraries and now a tree, verification just recursively verifies two things. One, that all expressions are product free and formed by registered atoms. And two, that sign, composition, and top level rules are satisfied. So we've seen the sign and composition rules. The top level rules just say that, one, that the actual objective is convex, and that two, the constraints all satisfy kind of one of these forms here. So you can have constraints that look like affine on the left, affine on the right. You can have constraints that are, convex is less than or equal to concave, because if you then move that concave over, you get convex minus concave is less than or equal to 0, which is our standard form. Convex minus concave is going to be a convex function, so it's great. You can't obviously specify the opposite and say something that's convex is greater than or equal to something that's concave. So to see an example of this, again, very similar to the example we went through together. You would form a tree of your objectives and your constraints, and you would go up keeping track of the convexity as you go. So x1 and x2 are affine. Min over these things is concave non-decreasing. Square root ends up being concave non-decreasing. What's 1 minus log? It's convex. And you end up with concave is greater than or equal to convex. Check. For the other constraint, you get affine equals affine. Check. And then for our objective, you get affine squared is convex. Check. So that's it. You know how to do verification. The cool piece here, I think, is canonicalization. So how can a library take all of these different things and then convert it to one form that you can then send off to solvers and just have them solve? That's very, very cool. So how do we take something that looks like this, or has our more general constraints from the last slide, and convert it to the canonical form, which is going to look like this. It's going to take a linear objective subject to affine equality constraints and then set constraints, which are going to be convex. And in reality, we're going to end up through the process of canonicalization with what is a partition canonical form, where different variables and constraints end up being grouped together, which ends up making solvers very efficient. Canonicalization is going to rely on two things. On one, linearization, and then where it's good for solvers, on graph expansion. So yeah, let's dive in. Linearization says the following. It says to take all of the product-free expressions and convert them to affine expressions with additional inequality constraints. So we introduce a new variable for each function v, so vj here, and then introduce a new constraint that says if f was convex, that f should be less than or equal to vj. If f was concave, then f should be greater than or equal to v. The second thing we'll do is whenever there is an inequality constraint of something that's affine on the left, we're going to give it some slack. We're going to introduce a slack variable, I think similar to maybe what was done in LPs, right? And introduce a slack variable where that s is greater than or equal to 0. Okay, so let's do an example. And let's just do the same one that we had before. So we had, I think it was like something like 3. This might be, I don't know, this might not be the same thing, but we'll try. Plus max of, I think it was like x of 1 minus log x2, something like that, plus x1 squared, x1 minus x2. The other thing we'll do here is whenever we have an affine expression, we'll introduce a new variable and set it equal to that affine expression. So what I mean by that is whenever we see just x1 minus x2, I'll just call this epsilon1 and introduce a constraint that says epsilon1 equals x1 minus x2. Okay. So let's start with linearizing this 1 minus log x2. So that's going to look like 1 minus v1 with the new constraint that log x2. So log is concave, so it's going to follow the second one. So log x2 is greater than or equal to v1. Okay. I'm going to call this epsilon2. So I'm going to introduce epsilon2 equals 1 minus v1. So now we have x of epsilon2 plus x1 squared. Let's linearize this guy. Now we're going to call this thing v2 plus v3. So this is both of these together. With what new constraints? So the x1 is going to look like this. It's going to look like x of v2, x of epsilon2 is less than or equal to v2. What does the other constraint look like? So we had that. We're introducing v3 in place of x1 squared.
X1 squared less than
Yeah. v3. Okay? We're going to call this thing epsilon3. So now we have max over of epsilon3 comma epsilon1. So 3x1 plus x2. So we're going to do one final step here. Call this 3x1 plus x2 plus v4. What's the constraint that we're introducing?
max of x1 3x1 minus
v4. Cool. And if this was happening inside an inequality constraint, for example, like if this was happening inside something like this, less than or equal to 5, then what we would do with that is we'd introduce, let's do it in a different color, I guess. We would introduce plus s equals 5, where s is greater than or equal to 0. So following this second piece. So that's linearization. Does that make sense? Oh.
Why does that not change
Yeah, that's a good question. It has to do with the fact that these compositions are non-increasing versus non-decreasing. There's a section in the book on this. If you, it's cool. Yeah. So I think it's like you can rewrite compositions over things that are non-increasing and by introducing a new variable, and it ends up being like the same. I don't remember off the top, but it's in the book. Okay, great. So the second thing that ends up being sometimes useful for different solvers is graph expansion. The idea behind graph expansion is to replace a convex function with a minimization over its epigraph. So what's cool is that the epigraph, or area above a convex function, including the convex function, is a convex set. And similarly, the area below a concave function is a convex set. So at any point in time, you can just replace this, the lower function in blue, as saying to find the y that minimizes the epigraph at each point in x. So doing the optimization on the right recovers the function f. So why might this be useful? So suppose you had something that looked like this. You had minimization over x of something with the constraint absolute value of x is greater than or less than or equal to 5. If you took its epigraph form, it's going to look like this, right? The epigraph of the set is the set where y is greater than or equal to x and y is greater than or equal to negative x. So if you take the graph expansion of this, you can replace this with the following constraints, with y is less than or equal to 5, y is greater than or equal to x, y is greater than or equal to negative x, and do an additional minimization over y. And this is the same thing. So these are equivalent, but you've suddenly turned this really kind of annoying constraint into something that's just a bunch of linear constraints. So you've suddenly, if everything else was linear, then this all of a sudden just becomes an LP, which is pretty cool. Okay, great. So that's it for canonicalization. The final piece, we'll just touch upon it here quickly, is solution methods. So you can imagine if everything ended up being linear or quadratic, you might just be able to dispatch to an LP or QP. Other common solutions include using interior point methods to solve this. So what happens when using interior point methods from canonical form is you convert the set constraints, which would include the inequality constraints, into a barrier function in the objective. So now you have this objective. So now you have this optimization function that's linear plus barrier subject to some equality constraints. And what's cool is that you can often solve this very efficiently using Newton's method. So the actual derivation of this is in exercise 14.7. But if you apply Newton's method, so do a second order Taylor expansion and then apply now the KKT conditions as well for the equality constraints, you end up with a set of linear equations over the next design point to try, so x plus delta x, as well as the dual variables. And if that Hessian on the top left there, the del squared p barrier, is if that's non-singular, then you can solve this with block elimination, first for the dual variables, and then for the next design point. So doing this, you can often get to a solution in just a few iterations. And what's cool here is that inversion of the barrier function, because we're in actually a partitioned canonical form, that is often very sparse and can be inverted very efficiently. So it's not an n cubed in x. It's often more like n or n squared. Okay, and that's it. So to summarize, disciplined convex programs is a convex optimization problem that can be automatically verified and canonicalized, making it amenable for efficient solvers. Convexity for a DCP requires that its expressions to be product-free and that they follow sign composition and top-level production rules. Not all convex functions are DCP compliant, but if you can make your functions with DCP, then you just should use disciplined convex programming and just get the right answer out. So behind the scenes, canonicalization is the process of taking DCP and producing a problem in partition canonical form, and then approaches to actually solve that problem can use interior point methods to do so very efficiently. Great. Any questions? Cool. And then with that, I guess we'll switch over to doing multidisciplinary.